Hello everyone and welcome. Today I want to talk to you about the dual nature of light and a groundbreaking phenomenon in physics, the photoelectric effect. There are some phenomena as interference and polarization which can only be explained by considering light as waves. On the other hand, phenomena such as photoelectric effect and Compton effect can only be explained by considering light as a particle. Today, we'll see what photoelectric effect is. Discovered by Heinrich Hertz and later explained by Albert Einstein, the photoelectric effect occurs when the light hits a metal surface and ejects electrons, as you can see from the image that I've drawn. Let's see what we have here. First, there is the energy formula of the waves. E equals to the product of the Planck's constant and the frequency of the wave. We can express the wave's energy this way thanks to the electromagnetic theory. When a photon of energy is incident on the surface of the metal, a part of energy, that is phi, and we'll be talking about in a second, is used in liberating the electron from the metal. This energy, or the Greek letter phi, is known as the work function of the metal, and it's the minimum energy for the electron to scatter away, aka the minimum energy for photoelectric effect to be observed. The rest of the energy that the photon had is given to the electron so that it acquires a kinetic energy. We all know what kinetic energy is. The equation and visualization that I made is called photoelectric effect. Formulaically, we can say that the product of the Planck's constant and the frequency of the photon, as we can see here, are equal to the work function of the metal and the kinetic energy of the electron. Thus, a photon's energy is completely absorbed, and there is nothing wrong with that actually. Light is not a matter, so it can be fully absorbed, and that doesn't violate any behavior of waves. But you may ask, you said that photoelectric effect can only be explained by considering a photon a particle. You're correct. Now let's get to the most interesting part. Thomas Young's double slit experiment made us believe that light is only behaving like a wave. But if we consider light as wave here in photoelectric effect, the effect won't be seen. Let's give some simple numbers. Now, let's see that the work function of the metal is 5 joules, meaning that the minimum energy for electrons to escape is 5 joules. If photons were waves, even if the whole wave had more energy than 5 joules, let's say it's 10, the whole wave, it wouldn't affect the electron because of the wave behavior and structure. Unfortunately, waves cannot concentrate on one point and they have the tendency to spread. So it won't be able to pour all of its energy at a singular point at once. But particle structures indeed can. Let's now see. If the energy of the photon is greater than 5 joules, let's say now here it's 10, and the work function is 5 joules as well. Now, when the photons reach the electrons, whole energy will be affecting a singular point at once. And with that, the idea of wave packets were born. But we'll be talking about wave packets in another video when we talk about individual and packet waves. But think this as a particle which doesn't have a mass, and its energy is greater than 5 joules. We said that it was 10. We would observe the photoelectric effect. Plus, we can say that the electron would have a kinetic energy of 5 joules from the formula. Now, the electron will scatter away. Now I will be drawing that. Here the photon, the electron. And because of the formula, we can work here. The 10 joules that photon has are now the 5 joules that went to the work function of the metal, and the 5 joules of kinetic energy that has went to the electron. But what if the photon's energy was equal or lower than the work function of the metal? I will be writing the equal, it won't matter anyways. Simply the effect won't happen because when it were 3 joules or 5 joules, I'm giving an example as I said before. If it were 3 joules, it wouldn't have the necessary energy to for the electron to scatter away. So the 3 joules would do nothing, or we won't be able to observe the photoelectric effect. If it were 5 joules as well, it wouldn't change a thing because, as we said before, the work function of the metal, so like the minimum energy for electron to scatter away is 5 joules, and if we were to give 5 joules of photon, we will get the kinetic energy of 0 joules, and that means that electron actually would not escape. So uh, even if it were 5 or less than 5, the result would be the same. But there is another thing that happens as well. Electron would absorb the photon no matter what. So when the photon here comes, now the photon here comes to the electron, it's the same thing. Like the work function is 5 joules, and let's say that the photon has 5 joules worth energy. Um, it won't have the kinetic energy to escape, but electron, as I said before, electron would absorb the photon no matter what. Uh, but if it was not enough for the electron to escape from its atom's nucleus, as in here, it will fully emit the energy back. And so it would to absorb the energy really fast. And because it weren't enough for the electron to escape, it would just emit it really fast again. And it will fully emit the energy, and that is actually why the colorful emission of some atoms exists. After electrons get the energy, they give it back because they are more stable in their old state, and in the process they create a beautiful set of images. So, today, we even talked about the ifs, and we can wrap it up now. This work not only provided crucial evidence for the quantum nature of light, but also earned Einstein the Nobel Prize in 1921. A fun fact, as I said now, that Einstein got the Nobel Prize with the photoelectric effect, it's a bit weird to me that he did get nothing from general relativity, not even the special relativity. Uh, because at that time there was not enough experimental evidence to directly confirm the theory. General relativity made many complex predictions that needed to be verified by observations. Maybe we'll talk about in another video. Um, and when Einstein gave his speech for winning the Nobel Prize, he was actually really upset because he thought that Nobel Committee didn't care about relativity. Then when he got up to the stage, he, in a sense, the Nobel Award for the photoelectric effect, talked only about general relativity during his speech. That was interesting for me when I learned that. So, in summary, the photoelectric effect is not just a cornerstone of quantum physics, but also a testament to how a simple observation can revolutionize our understanding of the universe. We can confidently say that it has sparked something greater. Thank you for watching. See you in another one.